Welcome. You're joining today's webinar with SCA with Raymond Woodward on Geosteering, the space between geology and drilling engineering. Before we start today's webinar, we'd like to ask a few questions about the demographics of our audience. We understand from those who pre-registered that we have attendees from Venezuela, India, Nigeria, Norway, Algeria, Canada, Peru, and of course the U.S. And so we'd like to know a little bit more about you. So we've got a couple of questions. If you look on your dashboard, you should see the opportunity to answer the first question: what's your primary discipline? So we're starting to get votes in now. It looks like there's a lot of geoscientists on the phone, and quite a few also petroleum engineers, a few petrophysicists. So we're getting a pretty good turnout. Most of you have voted now, so let me go ahead and close that poll and share the results. It looks like 71% are geoscientists, 25% petroleum engineers, and the rest are in petrophysics. Okay, so we have one more polling question we'd like to ask. So how many years of full-time experience do you have in the oil and gas industry? We're starting to get our answers quickly now. Looks like we have a good distribution. There's some in each of the levels. Most of you have voted now, so I'll go ahead and share those results. It looks like it's a good distribution, with the highest number being over 30 years experience, but quite a few in the other ranges as well. So thanks for sharing that information with us for our audience today. So I'd like to start by welcoming you. And this is the webinar, Geosteering, the space between geology and drilling engineering. Our speaker today is Raymond Woodward. And Raymond received his geology degree from Baylor and started his career at SONAT, working in the Austin Chalk. And from there, he continued to remain in the East Texas area, working as an independent consultant with BHL Consulting, and he's now got Foresight Geosteering software as well. So Raymond has made a number of presentations on geosteering over the years, including short courses, and has received awards from APG for best paper on his work in geosteering. So Raymond also teaches a course for SCA on geosteering, best practices, pitfalls, and applied solutions. And that's being offered in Houston in May and November. You can see the dates there. And additionally, you can schedule that class to come to your location in-house if you would like to do that. So contact us if you're interested. And we do have several webinars that we've already recorded in this webinar series. The next one coming up is Jim Smolin in April, and he'll be speaking on production logging, the modern well flow evaluation. So look forward to that opportunity. Again, SCA, in addition to training, we also provide consulting, direct hire services. We do projects and studies, and so look to us when you have opportunities for us to help you. So I'm going to give the presentation rights now to Raymond, and Raymond, we will ask you to start your presentation, please.
All right. Thank you, Susan. Let me arrange my screen just a bit. And while I'm doing that, thank everyone for joining us here today. I will move along as quickly as I can so as not to waste anyone's time. I entitled this the overall presentation, which was for the short course, the space between geology and drilling engineering, because it is truly and literally that. Geosteering as a discipline necessarily operates in the bridge space, if you will, between the drilling team members, the field personnel, and the geologists in any given effort. And it is important for all purposes to think of geosteering in those terms, and you'll hear a little of that today. Today's topic is going to be a look at survey, directional survey and precision, a phenomenon that descends from that called positional uncertainty, and then some of the possible causes, the possible impacts, and some practical responses to those things. This is just a subset of the short course, and this is not an exhaustive discussion on positional uncertainty and survey and precision. We just don't have time for that. But I want to share with you all some things that are well established and well known in the literature, in the industry, but not so often taught. So first we'll look at why this matters, the direct impacts on what we do. We'll take a look then at the most common causes for survey imprecision and positional uncertainty, roughly in an order of increasing magnitude, and then find some practical responses and best practices that descend from that. So now let's take a look at these cascading impacts. Why does this matter? Now, to start with, let me explain, I say cascading impacts because there is typically a sequential element to this, and it all starts like this. If our directional survey information is imprecise in any meaningful way at all, the first thing we start to see is that the geosteering interpretation violates the geologic model, whether pre-drill geology or post-drill, and you'll see an example of that very shortly. And from that descends a situation where the pre-drill directional plan is inappropriate. It has to be changed, which means a target change or several target changes that weren't anticipated and not always desirable. And that may quickly lead to borehole tortuosity, more doglegs than we want in the well. And that may lead to slower drilling, ultimately perhaps lower in-zone percentage, less of the lateral in the target zone. And along the way, a very important but intangible element that I captioned here as intra-team problems. In other words, confusion, misunderstanding, perhaps even some measure of strife or discord between geology team members, field team members, drilling engineering, and so on. And in a worst possible case scenario, we may end up with some unquantified degree of production loss. So these things matter. Now let's look at a real-life example of this business of violating the pre-drill and post-drill geologic model. This is based on, it is anonymized from an actual mid-continent well that was drilled some years ago by one of our software clients. And we were called in to help them understand what had happened. So if you look at that top panel, you're looking at a map view of a 3-lateral well in what's commonly called a pickle fork configuration or pitchfork. The regional dip here was roughly 1 degree to the right side of the slide. The laterals were slightly over a mile long from surface location, which is the little red box on the left. And regional strike was very well established as north-northeast to south-southwest. So they drilled the first lateral, this one on the north side of the slide. It wasn't actually to the north, but it's anonymized. And then they drilled the second lateral. It's labeled incorrectly as lateral 3. It should be lateral 2. They drilled the 2 outboard laterals first, and then they came back finally to drill the center lateral 3. And what they ran into right away was great difficulty making sense of the geology, because the center lateral appeared to be running, or the structure, the geologic structure in that center lateral appeared to be running appreciably low to the ones on either side of it, and too low for the structure map that they had drawn before they drilled the well. So the geosteering effort for that last and center lateral was really, really challenging for the operator. For the geosteering professional, there was a lot of discussion around their office about what is going on. And they did fortunately resolve to drill the target zone, which they substantially did, even though they couldn't make sense of the geologic structure. And the question was put to me, what happened? And the honest answer is that I don't really know for certain, but that bottom panel there is the most likely explanation. It was positional uncertainty, survey imprecision, that whereas that center lateral was probably actually depicted in green there in that lower panel, the directional surveys had them thinking that it was much lower. Therefore, since they knew they were in the target zone, but lower, the only conclusion they could draw was that the target zone was structurally much lower. Now let's back up to a summary slide of some of these sources of positional uncertainty here. A short selection. Let me start off by pointing out that bizarre S-curve in that well path in the center of the slide with a bright yellow circle around it, that's absolutely real data that came to me from the field, from one of our client operators. I loaded their surveys, it drew the well path, and I saw that. It is obviously not real. But on the first call to the field to ask them what the problem was with their survey, the answer was nothing, no problem, it's all good. So the takeaways are these. One, survey errors do happen, just plain old errors. Secondly, surveys are edited on location very often. We normally don't see that process. They've been edited before we get them. Third, they can be edited after we get them, and you'll see an example of that shortly. And fourth and most important, the surveys, directional surveys, are never as accurate as they appear to be. For example, most of us have seen directional survey files that present true vertical depth to the nearest tenth of a foot, certainly whole foot. They aren't that accurate, ever. And what we're about to see is a list of some of the reasons why. You might notice in the bottom of this slide a little box that says, whatever happened to the law of significant digits? You should probably all remember that from algebra class. The law of significant figures or significant digits says that in any calculated result, the outcome cannot be any more accurate than the least accurate input. As an industry, we violate that law constantly all the time. It's not an act of ignorance or evil. It's just customary. So let's start to dig now into some of the actual finite sources of the problems. First, a bit of a punchline, an overall punchline. It's been well established in the industry literature for a lot of years, and I've heard this from quite a number of directional drillers, that the error bars of the range of uncertainty and true vertical depth at the end of a mile-long lateral can easily exceed 50 feet of TVD. Now, remembering that geosteering is mostly an up-down question. In other words, we're too high, we're just right, or we're too low. You'll hear me talk much more about TVD than azimuthal left-right issues. This does not mean that the errors are there. This merely means that it's pretty well established that the range of possible error can exceed 50 feet of TVD at the end of 1 mile. And all of the sources that we'll look at here, and even a few more in the short course, any error that any one of them might introduce is additive to the others. So if we pick up, for example, 1/10 of a degree of inclination error on our inclination measurement, which we'll look at here in a moment, plus another few tenths of a degree of inclination error from another source, then statistically we have to add those ranges of possible error to each other to know the extent of our error bars. Quick note before we go any further. Notice in the bottom right corner of this slide a little blue box. For the purpose of this discussion, I will use the directional driller's nomenclature for inclination, and I will apply it to formation dip, because that's our habit here at BHL. So straight down is 0 degrees. Flat is 90 degrees, and straight up is 180. So, for example, 5 degrees up dip would be expressed as 95 degrees. I want to clear that up in case that's unfamiliar to someone. Do remember, through it all, I'm not saying that the error is there. I'm warning that it can be. So let's look at probably the first and smallest common source of error, which is simply in the measurement of inclination and azimuth in the survey tool. Now, over the years, these tools have gotten better. We've gone from single accelerometer and magnetometer tools to, in some cases, 6 of each. And so this range of error is shrinking, but this number has been around for a long, long time. And based solely on the accuracy of measurement of inclination, it's not unreasonable to look for 3 feet of TBD error per 1,000 measured depth feet of lateral. So, at the end of a mile-long lateral, 3 feet per 1,000 feet times 5,000 feet, there is a range of uncertainty of 15 TBD feet associated with that alone. Left-right azimuthal measurements, which are most commonly magnetic, almost always, the range of potential error there is slightly larger, closer to 5 feet of left-right uncertainty per 1,000 measured depth feet. And so this defines an oblate cone of error that increases as it goes out. Oblate meaning slightly flattened. Now let's look at what is estimated to be the source of 80% of all inclination measurement error, according to an SPE paper published in 2006, which is sag in the bottom hole assembly. This is a small to medium range influence. It may contribute perhaps 1 or 2/10 of a degree of inclination error as we go along at each survey if this is happening. And it is very dependent upon the bottom hole assembly and the stabilizers and how it is all arranged. But it is simply this. If you look at this slide, you notice we're drilling in this case from right to left. And let's say our directional sensors are roughly halfway between those 2 stabilizers, about where you see my cursor moving now. And I neglected to turn on the laser pointer for this purpose, but I hope I assumed that you guys can see my cursor. But if the stabilizers are spaced far enough apart and the bottom hole assembly is flexible enough, especially in a horizontal hole, then surveyed inclination in this part of the hole at any point as we approach the center of the sag, surveyed inclination will be too low. It's unavoidable if there is sag in that pipe. Contrast-wise, as we move further to the left, as we approach the next stabilizer, surveyed inclination may be 1 or 2/10 of a degree too high. And we won't know whether that is happening or not. The absolute truth is unknown and unknowable unless we go back in with a different survey tool and measure it again. Now, it's important to remember that in all cases, there are only 3 measured quantities in a directional survey: measured depth, inclination, and azimuth. Excuse me. Let me get a short drink of water. True vertical depth, TBD, is principally calculated from measured depth and inclination. So inclination error of any sort will manifest itself in a true vertical depth error of whatever degree. Typically it's very small. And I don't want to frighten everybody. It's not that all wells are beset with all these problems, but all wells can be, and some wells most certainly are. So, if we have an inclination error associated with sag in the bottom hole assembly, we're going to have a little bit of a TBD error. Any one error is very small and consequential, but over many dozen, if not perhaps 100 or 200 surveys, the range of uncertainty builds up as we statistically add all those things. Now let's look at another source, common source that's associated with bent sub drilling motors, which are the industry standard except where rotary steerables are now more increasingly in play. This is based on a really interesting study and paper that was published in the SPE in 2012, conducted by Ed Stockhausen at Chevron and a cohort who actually works for Schlumberger Anadrill. And what they observed, and they actually tested, is that as a bent sub motor is drilling, in this top left panel, because there is a minor bend in that mud motor, the hole diameter will be greater than the bit diameter. It has to be, because there's a bit of wobble in this bottom hole assembly, in the outboard end of it. However, when they stop and orient up, down, left, or right, it doesn't matter, and start sliding. In other words, the motor stops spinning and only the bit is spinning. Hence, the wobble at the face of the bit is gone. There will necessarily be, if you look in the larger bottom right portion, a little ledge where the hole transitions from overgauge due to rotating to bit gauge because they're only sliding. The net effect of that, insofar as survey precision is concerned, is that if the survey tool is somewhere draped across that ledge, whether it's an up ledge, down, left, or right, then it will skew the inclination or azimuth value a little bit. These also introduce what are increasingly in the literature referred to as micro-tortuosity or micro-doglegs. And we suspect, I haven't read any papers on it, but we suspect that these things may account for some of those occasions where production casing simply will not go to bottom, and we do not know why. Now, granted, hole openers, reamers, all those sorts of things, especially in softer target rocks, will wipe these things out over time. But our concern for today's discussion is impact on directional surveys. And they're there. What was interesting about this particular paper, this study, is that Stockhausen and the guys at Schlumberger poured themselves an enormous block of concrete and then drilled a hole through it, and then they slabbed it right down the axis of the well and took photographs of precisely this phenomenon. Okay, let's move along. The next source of potential problem I wanted to point out to everybody is most pertinent while we're drilling the curve, especially higher in the curve, and it has simply to do with how stationary surveys are taken. Now, granted, you won't hear me say much today about continuous surveys and all of that, because the stationary surveys are still far more common, and they've been around for decades. But here's how it's actually done, whether we're drilling vertically or horizontally. Typically, we will drill, if this is our survey sensor, let's say, in this bottom hole assembly where you see my cursor moving, typically they will drill anywhere from a few feet to as much as 20 feet past survey depth, and then pull back up to take the survey. The reason they do that is to relieve compression and torque in the drill pipe so they can get a more accurate survey. The problem is this: if we drill, for example, 10 feet past survey depth and pull back 7 feet and record that survey as if we had pulled back all 10 feet, then there is an instant 3-foot depth error. And the reason I say that is that most often surveys are taken at a pipe joint, at a tool joint. And those depths are already in the tally book. They've already been tallied. So if we know we're going to take a survey at a tool joint at, for example, 9,003 feet, if we drill to 9,013 feet and then pick back up to about 9,009 feet, we'll record that survey as if it had been taken at precisely the right place. And I've stood on the rig floors and watched it happen. This is most pertinent, like I said, in the curve, especially the upper part of the curve, because it will, even a small measured depth error will translate into a TDD error when we're more vertical than not. And in fact, counterintuitively, if you look at this slide, we have to get all the way out to an inclination of 60 degrees before half of that error is translated into horizontal displacement instead of vertical. In other words, down to a 60-degree inclination, this is a graphical depiction of feet of TBD error versus inclination, and here are the numbers in this right-hand panel. But until we get down to 60 degrees inclination, more than half of that measured depth error is translated into TBD error. And then the TBD impact goes away as we approach horizontal. Of course, once we're in the lateral, measurement error of this sort translates into northings and eastings and vertical section distance and so on. But it is the curve that is very often the most sensitive part of a well. And it is not uncommon. Like I said, I have stood on the rig and watched this happen, and nobody really gives it much thought. What's 1 foot here or there? Well, if there are many dozens of occasions like that, it might matter. And once the survey is taken, there is no way to know. It's in the books. It is recorded. Now, it's not just TBD error that may be introduced this way, because in any KBTBD-based geosteering system, and I'll define KBTBD-based here just very shortly, in any KBTBD-based system, TBD error will introduce exaggerated interpreted formation dip. Exaggerated formation dip is driven by even minor TBD or thickness variations acting over a very short vertical distance. Now, the vertical section distance, vertical section, big difference. Vertical section, of course, is a horizontal quantity. Vertical is vertical. Let me define KBTBD very quickly with a disclaimer that we did not invent this term, we just live with it. It's been around for a long time. And KBTBD is the mathematical transform, and it's really a mashup of trigonometry functions mostly. The mathematical transform of highly deviated and horizontal data into a pseudo-vertical log view, taking into account formation dip. Let me say that just a little bit different way, because that was a bit of a long sentence. KBTBD is a ordinary TBD log, but corrected for formation dip, that formation dip acting over some horizontal, so-called vertical section distance. And here's the net effect. Here's what I want everybody to see. At a short vertical section distance, high in the curve, say 50 feet out from under the rig. And by the way, if anyone's not familiar, 0 feet vertical section distance is under the rig by definition. Always, or it should be. But at a very short vertical section distance, a 1 foot TBD error will drive a 1.15 degree change in calculated or apparent formation dip. A mere 5 foot TBD error will drive a calculated formation dip change of 5.75 degrees if we're only 50 feet out from under the rig. And I've tried to illustrate it by the sizes and shapes of these triangles over here. So to accommodate, this is actually, the little blue box is actually a 10-foot box, just to make it show up. But to accommodate that 10-foot difference when we're this close to the drilling rig, it defines this triangle, in this case, of error. Now, this phenomenon goes away as we move away from the rig. 500 feet out from the rig, 500 feet vertical section, that 1 foot TBD change drives only a few, well, under 2/10 of a degree in calculated formation dip. We can just ratio down these upper numbers of 1.15 and 5.75, take 1/10 of that, and you'll be 500 feet out from under the rig. But the point is that any minor change or error in true vertical depth or thickness variation between the type curve that we're using and the section that we're drilling will culminate in an exaggerated apparent formation dip. This is why you may have seen geosteering interpretations that appear to show extreme formation dip under the drilling rig at short vertical section distance repeatedly. It is not that the math is errant. It is not that the algorithms fail. It is this short vertical section distance and trying to make up even a very, very small vertical variance when we have a very, very small horizontal displacement to work with. Now next, let's look at probably the most pervasive source of problem in the directional industry today. This is very, very well documented. This is the prime driver between the push for continuous inclination measurements and all of that. And let me start by saying that this is absolutely real data from a client's well, used strictly by permission and substantially anonymized. There's no way to know whose well it actually is. It is an unusual data set in as much as they actually surveyed this entire lateral, plotted in black, every joint of pipe, every 30 feet, 31 feet. I rounded it off to 30. So here comes the curve. The curve lands here. And they continued to survey every joint of pipe, roughly every 30 feet, all the way to the end of the lateral. However, since the advent of top drives that can handle stands of pipe very gracefully, it's far more common now that beyond the end of the curve, we survey only every stand of pipe, roughly every 90 feet. So, to replicate that phenomenon, I came back from the end of the curve here and plotted in blue only every third survey. In other words, 90 feet survey. And look what happens. Within 200 vertical section feet difference, in other words, 200 horizontal feet of displacement from the end of the curve, we've introduced a 2.5 foot TBD error versus the 31-foot surveys. By the time we get to the end of the lateral, 5,000 feet farther out, there is a 16.5 foot TBD error based solely on how often we did or did not take surveys. Now, in some cases, to explain the green data series here, in some really fast, uncommonly fast drilling wells, we see them occasionally but not often. Operators will stop to survey only every 2 stands, roughly 180 feet. So I replicated that in this green well path here. And there's several things to note here. First of all, it's all in what we never saw. We didn't have a survey to tell us that the well path turned this way or that. So we simply do not know and cannot assume. Second of all, the error that may be introduced here is truly random, and here's a great example of that. Notice at about 3,300 feet vertical section, which is 2,100 feet past the end of the curve, whereas the 180-foot surveys in green had been less accurate than the 90-foot surveys. Suddenly they trade places at 3,300 feet out. And now the 180-foot surveys are actually more accurate in depicting the position of the well path than the 90-foot surveys. It's the randomness of it that causes us some consternation. And again, if the surveys aren't taken, the truth is unknown and it's unknowable. If the data doesn't exist, that's just the end of it. It doesn't exist. Most wells we see now are surveyed only every stand of pipe, roughly every 90 feet beyond the end of the curve. And so if you're working on a well that appears to be a few feet too shallow or too deep, the formation that is, this is very likely the reason why. And as the lateral length gets longer, the range of uncertainty necessarily grows. Now, this is fairly well documented. There have been a number of talks and papers given on this. But one thing that I've noticed about this, and you can see here, I highlighted with the little red arrows. Let me check the clock real quick. The little red arrows indicate that not only is it the absolute true vertical depth of the wellbore that may be off, but notice that the inflection points, or the turnaround points, if you will, in well path inclination, where the well path goes, for example, here, from an upward trajectory and rolls over to a downward trajectory. The point at which that rollover occurs in the apparent well path can shift laterally, in this case, nearly 100 feet outboard. In other words, the 180-foot surveys didn't see the well path roll over until 100 feet after it actually did. That has big implications for how we interpret formation dip, and we're about to come to that. But you'll notice these little red dashed arrows at a number of places where these inflection points in the well path actually shift laterally because we did not have the survey data to tell us that the well path had turned over at one place or another. So in the next two slides, let's look at how that rolls into our interpreted geology. This is utterly diagrammatic. Two renderings of a well path, the same well path, hypothetical well path, let me say, in the upper case, assuming that we took surveys every 30 feet or closely spaced. So let's say our well path, and the little triangles represent the survey stations. So we see the well path come down and land at 90 degrees flat, then it wanders up, and 90 feet later is flat, wanders down, 90 feet later it's flat, inclination, flat again 90 degrees later, and flat again 90 degrees later. And yes, I created this illustration to make a point. This is not real data, but it very realistically illustrates the principle at work. But now let's take that same well path and leave out, beyond end of curve, the 30-foot surveys, and notice what happens. We land the curve, it appears to be flat, 90 degrees. 90 feet later, we see flat. 90 degrees later, we see it flat. And so it goes until we finally see the well path turn up. What we never saw was the well path wandering up. This gray line just reproduces the well path from above. So the only conclusion we possibly can draw is that the well path lands at 90 degrees flat and stays that way. We have no option but to assume that that is an accurate rendering of the well path, that it stayed at 90 degrees flat. Now, that has implications for the interpreted geology. Let's look. Same two well paths, but this time I've added a hypothetical monoclinal dip target zone. We see ourselves come down, land in the target, wander out the top, wander out the bottom, wander back up into the bottom, back out the bottom, and so on. The only way to explain this business of going out the top and out the bottom and back into the bottom with a flat well path is to twist or bend formation dip up and down. In other words, if this flat well path went out the top of the formation right here, the only way for a flat well path to do that would be if the formation turned down, but it didn't. What actually happened was the well path turned up, but we don't know it. The net effect is this, and this is something to watch for. Well path TBD error, and I'm reading from the blue text box, well path TBD error is always precisely and directly reflected in formation TBD error, and well path inclination error is always precisely and inversely reflected in formation dip. In other words, the well path went up, we didn't know it, so we assumed that the formation went down, and so it goes. And we may see this from time to time. You heard me, I'm trying to speed up here a bit. You heard me mention edited surveys, and this is an absolutely real data set from an Appalachian Basin well that we got from an operator, client of ours, who called to say ask us, well, we have 3 different sets of surveys for this well. Which one is correct? And I'll tell you the punchline now. At the end of the day, we had to tell them we didn't know. It was unknown to us and unknowable, which is absolutely correct. But here's what happened. To begin with, this is the same well path. This is the same well bore. The little dots are the surveys. The red data series that you see ghosted in the background are the surveys that came directly from the directional company at TD. The blue data series came to the operator via WITML feed while the well was drilling. And you notice out here, the well bore appeared to be 26 feet shallower, 20 odd feet shallower than the final survey set indicated. And finally, in black, there's a set of surveys that went to an offsite survey validation service and then to the operator, and it very nearly mimics the end of well data. Notice also not just that there are TVD displacements between where we think the well path is and therefore where we think the formation is. Notice that there are 4 surveys that are denoted by the yellow triangles that are simply missing from the while drill survey file in blue. Notice also there's 1 survey that's just simply flatly missing from the post-drill in red survey set that was present in these others. And the question again came to us, why was it deleted? Why are they not there? And our only honest answer is we don't know. We don't have any way to know. Finally, let's move on to the biggest single source of potential positional uncertainty or survey error, the big one. Is simply this, that every shred of depth data starts with pipe tally, and there are no exceptions. Granted, now there are drilling rigs with automatic pipe handling systems, and that is probably very helpful. But otherwise, it all starts with a rig hand and a tape measure measuring joints of pipe and writing them in a tally book and then punching those numbers into a computer. If somebody neglects, for example, a 6-foot crossover sub that should be in the bottom hole assembly tally, but they leave it out, then that is a 6-foot depth error. The thing to watch out for here, and the thing to always remember, is that if there is going to be a pipe tally correction, it's probably going to be when they trip pipe. And also worth remembering that very often pipe tally corrections are not advertised after they make them. In other words, these surveys may already be in our system, in our geosteering interpretation, and we're not informed. We have to figure out in many cases for ourselves that the pipe tally changed. So now let's move on to the last 3 slides, some best practices, if you want to call them that, some recommended approaches, some which are broad in general, but they're very realistic. These things descend from, these recommendations descend from these issues that we just talked about. First of all, in the overall sense, for the well overall, start to finish, we must always remember the main priority, which is to stay in the target zone. It is not our primary priority to prove the map's correct, nor to follow a directional drilling plan. Unless upper management says that is your priority, the money, the producible hydrocarbons are in the target zone, not in the plan and not in the map. The second important bullet question, and those first 2 will be repeated in the next 2 slides, is to ask questions relentlessly and communicate. Failure to communicate, in our experience, is the universal failure mechanism. Every bad outcome that we've seen involved, to one degree or another, a failure of communication. Put another, simpler way, almost every big problem today started small hours or days ago, and communication could have made it go away. Now, given that it's important, more important than anything else, to stay in the target zone, if necessary, even if we believe that the surveys have a problem, it is our strong recommendation to, quote, be wrong together with the drillers. In other words, if the drillers believe their true vertical depth is something, and we don't believe it. Nevertheless, our job is to give them a target vector or window that will keep them in the right target zone using their numbers. So if necessary, be wrong together and then sort it out after the well TDs. Always evaluate the data and quick check your TVD and vertical section in your geosteering software against that which is provided by the directional drillers. If your software does not calculate true vertical depth, vertical section, northings and eastings for itself, really just at the mercy of the directional company, which is not ideal, but as long as they're correct, you're correct. Always insist that you be notified of any pipe tally corrections or survey revisions, because in our experience, you may not be. Never issue targets based on seemingly extreme dip values. Always know when the rig tripped out of the hole, always. And to the extent that you can get away with it, always advocate for more closely spaced surveys. Just don't always expect to win, because more surveys take more rig time. And continuous survey tools cost a lot more money per day. And this last bullet, respect the driller's priorities whenever possible, is intangible, but it is very important. We'll talk more about it in the short course. As much as possible, work with those guys, because we are unavoidably working in a team setting, and cooperation between us and the drilling department has very real impacts on the bottom line and on the quality of our life and the enjoyability, if you will, of our jobs. Now, that's the overall sense. While we're drilling the curve, again, I repeat those first two bullets. Stay in the target and communicate, but you notice I added communicate preemptively, and what I'm saying there is this. You may quickly find that the drilling department is your best friend if you warn them beforehand of problems that you suspect are coming. This was something that I learned quite by accident 20 some odd years ago. But if you think you see a target change or a problem coming, go ahead and warn them, if the workflow within your office allows it, that this may become true. And they will love you for it. And they will very quickly become your supporter instead of your antagonist. Do beware of distant type logs, vertical type logs, and use near offset synthetic type logs if possible. Synthetic means pseudo-vertical KBTBD logs from a nearby offset deviated or horizontal well. And we can talk more about that in the short course. Use large segments of data. Avoid the pitfalls of micro steering based on tiny little short segments of data. When we're drilling the curve, we should always be slower to lower a target and quicker to raise the target for the drillers. And the reason is very simple. It's much easier for the drillers to land the curve and then drop slowly down into the target than it is to suddenly raise the landing depth when they're already near flat and in the process have to put a big upward dogleg in the bottom of the curve. And always hedge all your target determinations, especially in favor of the pre-drill model. What did the maps predict? And especially in the curves. Finally, in the lateral, those first two bullets repeat, because they are so important and we see failures associated with those so often. Added to that, observe the slides and where they slide and where they rotate if you're using a bent sub motor. And the humble, usually ignored ROP curve will usually tell us where they were sliding and where they were rotating, because rotating is so much faster. Always know also when they tripped. If you do need to revise a target, do it only as necessary, and to skip to the next to the last bullet, hedge the target change. It is the driller's priority to get the well drilled as quickly and cost effectively as they can. It is often our priority to stay 100% in zone. There needs to be a compromised position somewhere in between. Back to the slide, revise targets based on longer averages of true vertical depth and dip. usually several hundred feet of data or more. One short segment of data right at the end of the lateral is a risky basis for making a substantial target change. We already touched on hedging, and always, even though we're hedging in favor of the pre-drill geologic model, do be aware of any limitations in that pre-drill model. And we'll talk about that in a short course as well. Okay, I've almost exceeded my time here, so at this point I need to hand it back to Susan. That is
Thank you, Raymond.
Thank you.
So now we have a few minutes for questions. You can ask your questions using the GoToWebinar question feature. And of course, your questions will be anonymous, so this is a great chance to start asking your questions. While we're waiting for some questions to come in, I want to remind everyone that after today's webinar, you'll receive a link to the recording of the webinar so you can go back and view it again, share it with your colleagues. We'll send you an evaluation form and a link to registration details for Raymond's class on geosteering best practices, pitfalls, and applied solutions. That's offered in Houston in May and November. And the first question we have is, how do you know if a survey has been edited when you receive it?
You really don't, unless there is some other indicator. In other words, you've gotten a survey file and you then receive that file again with different outcomes, different numbers in it. You have no way to know. And I would stipulate, and this I hope, I prefer to believe is an extreme case, but I would stipulate this little story. It's absolutely true. I remember one morning standing in the directional trailer on a well location, watching the daylight directional driller tell the MWD guy to change the information in a survey because he didn't like it. And the MWD fellow said, well, no, we shot that survey twice and that information is correct. And the directional driller said, yeah, well, we're not going to send it to the operator, change it. And they did, with me standing there. I think that's probably rare, but I don't know. So the short answer to your question is, unless we've seen that same survey file twice, and it has different answers, we really have no way to know that it was edited.
Okay, the next question is it always a best practice to discuss the client on the pre-drilling phase to take short surveys, 30-feet surveys, to mitigate the error? So I guess that's a best practice on the part of the vendor with discussing it with the client.
Yes, it is. It is a great practice to advocate for more closely spaced surveys. I guess that was in this slide. It's not an easy argument or advocacy to win because it takes more rig time to take more surveys. The reason, the justification for drilling wells and surveying only every 180 feet is that they can get the well drilled faster. It's just that simple. But yes, as much as possible, advocate for more closely spaced surveys.
Next question. Can you talk about how the slide rotate pattern affects the error, the Stockhausen Effect?
Oh, I'm glad you brought that up. I started to include that in this presentation, but I knew I would run out of time. Yes, the so-called Stockhausen Effect is this: when we're drilling a curve with a dense submotor, which we normally are, more often than not, there are rotary steerables that can generate doglegs bill rates fast enough to land the curve, but they are more expensive. Here's what happens. If that bottom hole assembly will drill in a slide mode a curve that lands at the right depth, they will slide the whole way. And we'll take surveys, typically every joint of pipe every 31 feet, and we'll get a reasonably accurate rendering of true vertical depth at each survey. However, if the bottom hole assembly is overbuilding, they'll have to rotate, they'll stop sliding and rotate what we call tangents every so often. In other words, instead of building angle, we'll drill at a more or less holding angle. what happens is this. The minimum curvature calculation that pretty much everybody uses to calculate true vertical depth assumes a constant rate of curvature between the surveys. So let's break it down to an example. If we take a survey and then we're building a little too fast, so we rotate half of a joint of pipe and then we go back to sliding. The minimum curvature calculation that gives us TVD at the end of that rotate and then slide assumes we were sliding the whole way, and it will give us a true vertical depth answer that is wrong. In that illustration, we would actually be deeper than the calculated true vertical depth says we are. And it can add up to quite a few finite TVD feet at the base of a curve. That's something that I wanted to include to talk about in the short course, but I left it out here. But yes, that's very real. And it all has to do, to try to wrap that up, with a bottom hole assembly that's building angle a little bit too fast. So they rotate tangent, then slide, then they rotate, then slide, then they rotate, then slide. When they do that, rotate, slide, the minimum curvature calculation that gives us TVD will give us, depending on how much they rotate, an errant or incorrect TVD at each survey.
Thank you.
And by the way,
can you talk? Go ahead.
Oh, go ahead. No, I was just going to say it also matters. I need to hush. Go ahead, Susan.
Can you also talk about the relative costs of the different intervals being surveyed, 30 feet versus 90 feet versus 180, and I guess versus continuing surveying? Is it an order of magnitude, or how do those costs vary?
Well, I'm not well equipped to give you a good, accurate answer on the cost of continuous inclination or continuous survey tools. I need to update myself on those numbers. They are substantially more expensive than the conventional bottom hole assemblies. When I say substantially, I probably mean twice the daily cost to have those tools in the hole. As far as the actual cost in rig time of taking more stationary surveys, my argument has always been that there is a grievous false economy in saving 15 or as little as 5 or 10 minutes per survey and drilling a hole inaccurately. But you can approximate that each stationary survey takes the rig about 15 minutes or less. And then if you look at the daily cost for that rig, you can ratio that down. But there is a relentless push now, especially since the advent of the resource shale plays, which are very, very, very cost sensitive. There is a relentless push to go faster, do it less expensively. So it's a challenge.
Absolutely. So I guess the question is, how do you convey the value of the information to the client to make sure they understand what they might be missing out on?
Yes. That's been a soapbox of ours for many, many, many years. What did we really save if one sidetrack of a hole may cost $200,000 or more, open hole sidetrack. One frac stage gone bad would probably cost somebody in excess of $250,000. So how much money did you really save by cutting corners on surveys? But that's the operator's decision, not ours.
Absolutely. Well, thanks so much for your time today, Raymond. As a reminder to our audience, later today you'll receive a link to the recording of today's webinar, an evaluation form, and registration details for the class that Raymond Woodward teaches on geosteering, best practices, pitfalls, and applied solutions. That's offered in Houston in May and November, and we can also schedule it at your location at a time of your choice. Thanks for joining us today. Goodbye.